Hi everyone, my name is Jeroen. I'm a software engineer at Facebook, currently working in the source control team, and I'll be talking a little bit more about code search at scale. So we'll start things off by analyzing why programmers search. And the idea there is to signify how code search is integrated into many different developer activities, ranging all the way from exploring code to refactoring code to even debugging why a production service might be broken. After we've enumerated a couple of common search use cases, what we will do next is take a look at some of the problems that might arise when you try to search through huge code bases. And then finally, we'll take a look at some of the tools that we've built at Facebook to work around these problems of scale and to enable these common search use cases for engineers. So the first question is, why do programmers search? And there's many different reasons, because code search is a fundamentally important part of any efficient developer workflow. As a software developer, you often spend more time navigating through code, searching through code, than you actually spend on writing new code or changing existing code. And so what that implies is that in order for you to be an efficient software developer, and even in order for your software organization as a whole to be effective, you have to have the right tools to allow you to find code fast. And what we'll see throughout this presentation is that finding code fast isn't limited to just finding all occurrences of a string in a code base. If you want to build truly powerful code search, then you also have to think about stuff like querying semantical relationships or even searching through commit history. So as I mentioned, there's many different reasons why programmers search, but what we will do is we will take a look at 5 common ones. First, there's changing codes, where, for example, you want to change the implementation of an existing API, and in order for you to be able to do that, you have to know where the code lives, so that you can open the relevant file or files in your editor and start working. Secondly, there's exploring code, where you might be looking at trying to better understand a program that's lacking documentation, or you might want to write some new software and get some inspiration from existing code throughout the code base. Then there's refactoring code, and what I mean by refactoring code and where it's different from the changing code use case, with refactoring code, you are, for example, trying to change the name of an internal API, and in doing so, you want to make sure that you also update all of the existing call sites to it so that you don't break any existing code. And when you're using code search to find all of the existing call sites, you only want to find call sites to that particular function, not, for example, to functions with the same name but in different namespaces. Then there's also understanding code, which is less conventional search use case. With understanding code, you're looking at some confusing code, and you're trying to get some more context on why that particular code is what it is and why it was added to the code base. And then finally, there's debugging code, where you are, for example, faced with a breakage of one of your production systems, and you're trying to find the commit that introduced the breakage by using code search. So searching at scale, when you are working in a small repository, when you're working with a small code base, then search is still something that can help you out, but it's definitely less relevant. A lot of the times when you're working with small code bases, you feel familiar enough with the file system structures where you can easily navigate around without really having the need for code search to kind of help you out and be more effective. Now, as repositories grow, as code bases become bigger, code search becomes increasingly more relevant because there's just more code, there's more files, and you want to be able to quickly filter out the code that is relevant for you in that particular scenario. And so when you're working with medium-sized projects and even larger-sized projects, existing code search solutions such as grep or find can really bring you a far way. However, the problem with these tools is that at a certain point of scale, for truly large repositories, they just stop working. They aren't performant enough anymore. And it's at that point that you as an organization have to start looking at building some custom solutions to work around these problems of scale. And so that's exactly what we had to do at Facebook. So as the earlier speaker mentioned, The Linux kernel is a big repository. Last time I checked in preparation for this presentation, it was checked in at about 17 million lines of code across 60,000 files, which is big. It's often the repository that a lot of people associate with as the biggest repository they know. But with thousands of commits across hundreds of thousands of files, and even more, the Facebook's main code repository really dwarfs that. And so to kind of give you an example of what I meant earlier with certain tools stopping to scale at a certain point, if you want to do a simple grep query over the Linux kernel, which again is a big repository, it will always give you an answer in less than a second. That's fair. However, if you want to do that same query over Facebook's main code repository, it becomes quite intractable. It will easily take up to a minute and even more. So now that we kind of understand Facebook Scale a little bit better, and now that we've seen a first problem of Scale, namely performance regressions, let's take a step back and discuss the earlier enumerated search use cases in a little bit more detail so that we better understand them before we talk about some of the tools that Facebook has built to enable them. This will also surface some other problems of Scale that occur at Scale. So the first one was changing code, where you are, for example, trying to change the implementation of an existing API, and you want to find out where that code lives using code search. So as we mentioned, when you're working in a small repository, you might have an easy enough time to just quickly navigate to the file that defines the function that you want to change. But when you're working with bigger repositories, this becomes trickier, and you really need a code search tool that allows you to quickly translate arbitrary code tokens, such as function names or class names, to the containing file. Ideally, you also want to integrate such a tool with your other developer tools, so that, for example, you can quickly open a resulting file from your search query in your editor of choice, and you don't have to spend a lot of time just navigating through the code base, because that's time that is kind of being wasted. You want to spend time on actually working, writing code. Then exploring code, where if you think about it, writing software often is about finding the right pieces and making them work together. And what can really help you move fast there is having the ability to quickly find where some of these pieces are being used at different parts in the code base. And code search can really help you achieve that. It's actually probably one of the most popular search queries that we have at Facebook. And so in order for us to really make our engineers efficient, we need to have a tool that allows this kind of search use case to happen fast. And again, existing tools often just have trouble with the performance side because the code base is too big. Then refactoring code, which is a different class of search use cases. So with refactoring code, what we were trying to do is we are trying to, for example, change the name of an existing internal API. And as we do so, we want to make sure that we update all of its call sites accordingly so we don't break anything. Now, the problem with using naive code search to achieve this use case is that the function that you're looking for might also be defined in different contexts, or maybe some file uses the name of that function as a variable name. That means that if you use naive code search, you will end up with a lot of results that aren't really what you were looking for. And so you still have to spend a lot of time manually filtering them. Ideally, the search takes care of this for you. And so what can help you there is having more semantical aware search, where you can specify queries like, hey, I want to find where this function is being used, but not just this function name, this function on instances of this particular class. That way, you no longer have to spend time manually filtering out results. And this especially becomes relevant in big code bases, because if there's more code, the possibility of having irrelevant results obviously also becomes bigger. Then understanding code, where you are looking at some peculiar code and you're trying to better understand why it was added to the code base. Let's say that you are, for example, looking at a --" debug flag in the code, and you know that with or without that flag, the code would act the same, but you're interested in why it's there. There must be a reason. Now, a lot of software organizations, including Facebook, use elaborate code review tools. And what these code review tools do is they store a wealth of information for each commit that was added to the code base. This information includes metadata such as a summary, a commit name, the name of the author. But it also, these code review tools, they also allow you to add comments. And so, for example, when this code that featured this --debug flag was added to the code base, a reviewer might have asked the author, hey, why are you adding this --debug flag? And the author might have responded saying, oh, it adds some more verbose output that we are logging somewhere. And you can probably argue that the author should have put this as a comment, but he didn't. But at least the context is somewhere. It's in the commit. And if we open that commit in the code review tool, it's super useful because we have all of this context and it can help us better understand arbitrary code. So in conclusion, it would be super useful if we could, for any arbitrary piece of code in the code base, have a code search tool that quickly allows us to translate that code to the commit that introduced it, so we have all of this contextual information available. Then finally, debugging code, where your production service might be broken and you're conjecturing that it's probably because of a recent commit that was added to the code base, and you're trying to find this commit. Now, when you're working with a small code base, then a strategy that's feasible is just walking through commit history until you find the bad commit, because there just aren't many commits. Commit throughput is low. You can just manually kind of go through this process. However, as repositories become big, this also means that the commit throughput increases. And if you have a high commit throughput, just casually walking through commit history all of a sudden becomes less feasible. There's just too many commits, so you can't just walk through them. And even bisecting can become a little troublesome because the commits that you are looking at, you're not sure if they have anything to do with the breakage, so you have to be really careful when you're inspecting each commit. So at the same time, before I jump to Facebook's tools, a little bit more about, let me go back. So at the same time, production systems often have, or at least they should have, detailed logs for when things go wrong, for example, stack traces. And what would be super useful is if we could use the information in those logs, for example, in a stack trace, the name of the file where the exception was thrown, if we could use that information to search through commit history to quickly kind of pinpoint where the commit is that probably introduced our breakage. Okay. Yeah. So now that we have kind of spoken about these different use cases, and so now that we've seen a couple of the problems that arise when you try to apply them at scale, let's take a look at some of the tools that Facebook has built to work around these problems so that our engineers can use these search use cases. So the first tool that I'm going to talk about is called Dipgrep, and as you might imagine, it's our replacement for grep. So what Dipgrep allows you to do is it allows you to do a regular expression match over the latest version of our repositories. It's kind of the de facto internal code search tool. It's tightly integrated with a lot of developers' workflow. And the reason why it's so popular and why a lot of people use it is because it solves lots of different search use cases, but also because it's very fast. Queries typically take less than 250 milliseconds, which is better than the minute that grep would give you, as I earlier mentioned. And so the thing that makes Dipgrep fast is the fact that it's backed by a server-side index. It's basically a distributed system that consists of a couple of different parts. So first, there's the indexer. The indexer is basically a big machine that contains a checkout of all of our repositories, and it keeps them updated with master. Now, very regularly, what it does is it spawns an indexing job. And this indexing job, what it does is it indexes the latest version of each repository, and it dumps it to a distributed store, cluster.fs in this example. So at the same time, we have some slave nodes, and what these slave nodes do is they regularly poll cluster.fs and they ask, hey, is there a new index? Has there a new index been published? And if that's the case, they will download that new index, swap it in, and swap out the old index that they were serving from. At the same time, we also have master nodes that are polling cluster. And whenever they see a new index, they don't download the full index, but they only download a small piece of metadata. And they will later use that metadata to route client requests to the appropriate slaves. At the same time, there's also a pruner. And what the pruner does is nothing more than just prune old indices so that cluster doesn't grow indefinitely. So the master nodes, what they are is they are basically the service part. So it's the part that the clients talk to. Client requests can come from many different sources. They can come from our GUI. They can come from integrations with many of the other developer tools that we have. They can even come from a CLI. So the request ends up with the master. What the master does is it uses this little piece of metadata that it has stored to reroute the request to a bunch of different slave nodes who are all responsible for handling part of the computation. They then, the slave nodes, send the data that they're responsible for back to the master, who aggregates, packages everything nicely up, sends it back to the client. So as I mentioned earlier, Dipgrep is a popular internal service, and so if it goes down, then people will complain. So what we want is we want Dipgrep to be as closely as possible to 100% availability, obviously. Otherwise, people start complaining. And so usually when a service becomes unavailable, it's because some machines are having trouble. Maybe the load is too high, or maybe they went down. And so a way that we are trying to work around that problem is we spin up a bunch of different master and slave instances all over the world. At the same time, we also try to limit the dependencies that Dipgrep has on other systems, because these other systems might have a different SLA, and we don't want Dipgrep to go down because one of these dependencies goes down. And so all of this has made Dipgrep a pretty stable service, but it's not perfect. Nothing is perfect. And so to give you guys an example of how things can always go wrong, we recently had a couple of people at the same time complaining that Dipgrep appeared to be serving stale data. And so as we were debugging this issue, we figured out that a hardware issue at the cluster level had caused all of the new indices that were being published by the master to have a corrupt timestamp. Now, this timestamp is what the slaves use when they ask cluster if there's new indices available. So what that meant was the slaves weren't picking up any new indices. So to kind of hack our way around the problem as we were fixing the root cause, we encoded the published timestamp in the file name, which represents the index, and we patched the slave so that they could read this new format. We obviously fixed the cause at the actual hardware level later, but this just goes and shows you how you can feel like you have your dependencies under control, but then something low level like file system level corruption comes and bites you anyway. Cool, so Dipgrep is great. It covers lots of different search use cases. Regular expression match is really something that brings you far, but it doesn't solve everything. So one of the things that Dipgrep doesn't allow you to do is ask, hey, can you give me all of the callers for this function? More generally, it doesn't allow you to query any semantical relationships that might exist. And so this is where Codebreath comes in. Codebreath is basically our generic platform for efficiently storing and querying semantic information on code bases. So the Codebreath indexing pipeline runs about 2 times a day, and it starts with the index runner. What the index runner does is it tells the writer tier, which is a thrift service, to get ready for a new indexing run, which basically means flush your buffers. Then the index runner grabs all of the build targets for the repository that it's indexing. It then spawns a variable amount of build jobs, which we will call the worker tier. Now, the worker tier, each build job in the worker tier gets a set of build targets, and each build target consists of a set of source files. Now, you can look at a build target like an application. And so each build job is kind of responsible for building a set of applications. As the build job processes a build target and processes individual source files, it outputs an abstract syntax tree in AST, which we then process to a writable format. After we've done that processing, we dump it to the writer tier. Now, even though we process individual source file and create individual ASTs, we still end up with a global code graph because as we create and as we process these ASTs, we assign semantical hashes to each component of the AST, and so they can refer to each other. So the writer tier is receiving all of these processed ASTs, and it buffers them until it receives everything. It also does normalization and deduplication, and finally builds a new SQLite database, which represents a new index. Then dumps that index to NFS, and then we have the service part, which we actually call Codebreath, which regularly polls NFS in the same way that we did with Dipgrep for new indices. When it finds a new index, it will pull it from NFS, swap it into RAMFS, swap out the old index, and client requests, which can again come from many different sources, will start seeing results based on the new data. So with Codebreath, we basically end up with this global semantical graph that we can ask a lot of different interesting questions. For example, where's this token defined, which allows you to implement functionality like jump to reference, which you can find in many popular IDEs. It also allows you to ask questions like, who calls this token and what does this token call, which, for example, allows you to build a dependency graph, which is very useful when you're trying to better understand code and you're trying to kind of see how different components work together. Another interesting use case that Codebreath has is that it allows you to find dead code and unused imports. And a nice win that we were able to have there was that we were able to use Codebreath to retroactively search for, find, and remove unused imports, which allowed us to remove the size of some of our applications. At the same time, whenever engineers put up new diffs, we run Codebreath on that diff, and whenever we see an unused import, we will automatically tell the engineer, hey, this line has an unused import, you probably might want to amend your diff before you actually push it to the source control servers. Then the final tool that I briefly want to go over is Dipgrep. And Dipgrep complements Dipgrep in the sense that Dipgrep allows you to search through files, and Dipgrep allows you to search through commits. So what it does is it allows you to find commits based on content. What you do is you give it a string, and this string represents code that was either added or removed to the revision or revisions that you're looking for. You can optionally apply some filters. For example, you might only be interested in commits by a certain author, and then what Dipgrep will do is it will output all of the matching revisions. And the number one use case for Dipgrep is that it allows you to blame code fast. Now, many of you might be thinking that these existing version control systems like Git and Mercurial, they already have a blame operation, and that's true. And just for completeness, what that operation does is it maps each line of a source file to the last commit that touched it. And that's great, but there's a couple of issues. Number one issue, and the biggest issue, and the kind of recurring issue that we're seeing at scale is performance. It just gets too slow for huge repositories. Secondly, it also doesn't filter code mods. When you're working with huge code bases, a lot of commits are code mods, and code mods are most of the time commits that you're not interested in. They move stuff around or they rename certain function names. And so when you're interested in blaming a line, you're interested in better understanding that line, not a commit that just moved it around. And then finally, blame doesn't give you very high granularity. So with blame, what you can do is you can say, okay, what's the last commit that touched this entire line? But you might be interested not in the entire line, but only part of that line. And that's what Dipgrep does allow you. All right, so Dipgrep is a system that we've built on top of Elasticsearch. So writes are coming from either Fabricator, when commits are being created, or changed, or landed. Then there's also an indexer, which allows you to retroactively index diffs. For example, in the case of a disaster, or if you want to just index on demand. And then finally, we have a normalizer which runs regularly in search of missing revisions, for example, in the case of transient write errors in the fabricator component. Then writes are coming from many different components, including, again, some of the tools with which we've built integrations, or from our GUI, but they all go through our kind of generic search API. All right, and that's kind of it. So to conclude, code search is more than just matching a string. If you want to build powerful code search, you also have to think about stuff like querying semantical relationships and searching through commit history. Secondly, Scale requires custom solutions. We've enumerated a couple of popular search use cases, and we've seen many different problems of Scale. The biggest one is performance, but there's many other ones. And if you want to solve all of them, then you'll probably have to invest in some custom tooling. And then finally, if you integrate search with your other development tools, that's when you really make it shine. Thanks.